there's a subleading self-graviton theorem, and the existence of such a theorem, which is universal and the structure is completely fixed just by symmetries, that I use that to prove the existence of a stress tensor.
You're assuming some things here, such as finitely many particles of given spin. For example, this proposition would not hold in a higher spin theory, for example, necessarily, would it? Weinberg, in his soft photon and graviton theorems, did not possibly think of infinitely many higher spins, did he?
I don't think his derivation
don't
of
even
the
exist.
No, his derivation of the soft photon theorem doesn't care about other particles.
In fact, it results in ruling out high spin interactions.
Yes, but I'm not making that statement.
Okay.
Maybe you can have those additional things and some other non-trivial loopholes are present. But I'm only going to use his first statement, which is that there exists a soft photon theorem. Anything else that he concluded beyond that with additional assumptions, I would not need. So in principle, yes, holds for higher spin theories also. In fact, now that we know where the soft photon theorem is coming from, it's really just coming from symmetries, some asymptotic symmetries, which is a generic property of any theory that has gauge invariance. I don't even need, it could be some complicated theory. It could be just Chern-Simons without, like 3D Chern-Simons doesn't have a photon, but it has gauge invariance. So there's a sense in which there's no soft theorem, of course, because there's no dynamical photon. But the symmetry exists. You can write down its word identity, and it has non-trivial consequences for any S matrix that you want to consider and study. Okay, so let me first tell you what is the soft. So I'm going to start with the soft photon, which basically qualitatively captures all the things I want to tell you, and then the soft graviton is just the same thing with extra indices. So the soft photon theorem is the following. So I consider an S matrix in which I have one photon, Q. So now this photon has an A index, because it transforms as a vector under SOP. And I have a bunch of other operators. And the statement is that if I take a Q goes to 0 limit of this quantity, that the leading order term in this limit has the form K epsilon A over Pk. So that's a factorization of amplitude. So this is one quantity over here, and then it factorizes in this software. And there are other terms. As you can see, this term is order 1 over Q. There's a Q pole. So this is called the Weinberg pole. And there's other terms over here. These, by the way, also have currents, but I'm not going to talk about them. They're also universal. The leading term here is also universal. But let's not focus on that. Okay, so this is something, again, you might study in QFT. Now let me just use my parametrization, all of those things that I've already told you, and just rewrite everything in terms of omegas and x's. And finally, what I'm going to do is to get rid of this pole. So this is a 1 over omega pole. Let me define SA, which is not just a function of x, is limit omega goes to 0 of omega times OA of omega and x. So I multiply by omega, get rid of this pole, and then take an omega goes to 0 limit to get rid of all of these extra terms. So only this term is picked up. So then you can show that this insertion of SAX, this is simply has the form del A So the first thing I'd like you to immediately notice is this is true, that del A as B minus del B SA. Insertions of this thing is identically 0 without contact terms. This means I can just, as an operator, at the operator, I can just solve this. I can just say SA is del A of something else, S. Insertions of S are just this. So firstly, you see automatically that the soft photon, I'm going to call SA as the soft photon operator. The soft photon operator does not have D independent polarizations. It only has one polarization. All of them are related to each other. So this is an interesting fact. There's only like the energetic photon has depolarizations always, but the soft one only has one. Okay, so this is just the insertion of this operator. Another thing I'll ask you to notice is the dimension of S. Well, I'm always going to write delta of S and spin J. Well, its spin is just one, that's obvious. And by this I mean the spin under SOT with respect to the conformal group. And its delta can also be worked out very easily because remember the D operator, roughly speaking, delta was roughly minus omega del omega. So SA by construction is picking out the 1 over omega pole. So 1 over omega is an eigenvalue of omega del omega minus omega del with eigenvalue 1. So it has eigenvalue 1. Okay. My goal is going to be now to take this operator and construct a current, a U1 conserved current. What is the spin and angular spin and delta of a current? It's D minus 1 always and 1, right? So at this point I could just guess what the relationship has to be between these two things. It's a shadow transform, right? If you know in a CFT, a shadow transform is some non-local transformation that takes operators which have dimension delta to operators with dimension D minus delta without affecting the spin. So then I guess a shadow transform. We'll see that's the right answer, but let's not guess. Let me actually prove it. So prove it is easier to sort of do the reverse procedure, which is to start, let's say, what do I mean by a current? What I mean by the current is an operator J which satisfies the following equation. JB. Notice that I've already established that these are local operators which are conformal primaries. So I know by just the word identity what is the insertion of divergence of J in the presence of other primary operator. This is something, this is just a usual word identity. So it has to be QK delta x minus xk. So that's what it has to be. I want to construct an operator that does this, starting from there. But it turns out, as is very clear, the inverse process is much easier. I can start from this, multiply both sides by log, then this delta simply becomes a log, and then integrate. So this side matches, and then I just identify the operators on the right hand side. And so you can show that that's actually the shadow transform. So for instance, what I'm basically saying is you take del B, JB, I multiply, so this is at y, multiply by x minus y squared, and then integrate over, and there's a del A. So what I need to multiply by is an A derivative of log, and then integrate over y. This thing is, by definition, SA, right? Is this clear to everyone? Okay, I just integrate by parts over here. Del A del B log is just IAB. So this thing, on this side, I can just simplify it to, again, I'm not keeping track of overall numbers, it's just JB, Y, IAB, x minus y over x minus y squared, which I'm going to write as D minus D minus 1. This is the definition of a shadow transform. So this tells us that SA is the shadow transform of J, but this also implies that the shadow transform of S is J.
And what was IAB, by the way?
IAB is the conformally invariant stress tensor, delta AB minus 2 XA XB over X squared. Okay, so you can show this transforms precisely like a conserved current. It has all these dimensions, and by construction, it satisfies the correct word identity of the current. Okay, so that's the construction. We've sort of done it by hand and created it. Why should we not Should we be surprised that it's a shadow transform? Why should it be maybe not obvious, but now that we know the answer, let's try and understand it from a different perspective to make sense of it.
Why should I be excited already at this equation?
Well, this tells us that every time I have a bulk theory in which I have a photon, I have a conserved current on the boundary. Now, so far I've only told you about single insertions, but multiple insertions of J in a CFT are a lot of it is fixed by symmetries. In fact, if I was in a 2D CFT, I just need to know the OPE structure. So I just need to know the OPE structure, and I can tell you multiple insertions of J.
Is this a non-perturbative statement?
It's a totally non-perturbative
CFT.
Well, the starting point, of course, was the soft theorem. That happens to be a non-perturbative statement. That's exact. Therefore, this is not exact. Now I can extend this. I can consider multiple insertions of J from a CFT side, which we know how to fix by using OPE and all of these things. But as I've just told you, an insertion of J upon doing a shadow transform should just tell us about the structure of photons on this side. Now you might say, well, it's not just photons, it's only the soft photon. That's not enough. But remember, we also have translation symmetry. The translation symmetry takes omega and shifts it. So by knowing insertions of J and using translation symmetry, we can also determine insertions of other photon operators of other energies. We can really build it up if we use all of the symmetries that we have in hand. In 2 dimensions, this is especially powerful. This is where it was first discovered. But 2 dimensions, we have additional issues with infrared divergences. So I'm bypassing that, but those have been actually understood. It turns out in the presence of infrared divergences, well, this is actually nice because the soft theorem is actually exact, even in the presence of infrared. Even though this side is infrared divergent, and this side is infrared divergent, but this statement is exactly correct. So everything I've said so far is true. But the next statement, which is about stress tensor, the subleading Self-Graviton theorem actually does receive corrections, infrared divergent corrections, but it's already been understood how to incorporate them into a modified definition of the stress tensor, which is no longer just shadow plus some infrared divergences, but it can do that. Okay, so why should we not really be surprised? It's basically just for the reason I sort of described over here. So another way to sort of understand this entire structure is to just consider these sort of foliations and reduce all the fields in my theory in the tau direction. Do a KK reduction. And if I do that for a photon, you will find that the mass, so as I said, I do it for a massless photon in 4 dimensions. When I reduce it, I'm going to get infinitely many fields, most of which are massive in the ADS. The mass happens to be, if you can work it out just for f mu squared, the mass happens to be precisely omega squared, that omega over there. So the mode which has omega equal to 0, the soft photon, is massless, and should therefore give rise under this ADS CFT map to a conserved current that lives in this boundary here. And what is the relationship between the conserved current and the dual operator and an operator? Is the shadow transform. So it's precisely that.
Omega was the dual of null and transit.
I did say it was the null time, but under this ADS CFT map, it's sort of dual not just to omega. It's like omega plus something else, but omega equal to this omega equal to 0 is the same as that omega equal to 0. For that purpose, it works. Okay. So is this the shadow? This is interesting that the shadow happened to show up here, and I think it sort of begs a larger conjecture, which is that the operators in the CFT are all shadow transforms of the bulk operator. And one guess for why that maybe should be true is that the operators on this side, these look at the possible eigenvalues of D. Eigenvalues of D, because of this minus sign, unfortunately, are all negative, right? Because the O's is a scattering amplitude. Let's first take the simple example of a tree-level scattering amplitude. It has a soft expansion, and we know Weinberg has told us that the highest divergence you can have is just a pole. Everything else beyond that is. So if it was a tree-level amplitude, it's literally just a Taylor expansion, 1 over omega plus higher order terms. Let's focus, for instance, as just an example, is the omega squared term. So there's an operator that's sitting at omega squared. but the omega squared has dimension -2. So all of these operators have negative dimensions. But the shadow transforms, by definition, will then have positive dimension because it's always d minus delta. So conjecture would be that in the CFT, the nice set of operators that are really local, like when I'm taking shadow transforms, I'm not really mapping a local operator to another local operator. There's two operators which are happen. One of them is you should define as local, and that has local correlation functions. And the conjecture is that it's really these J's, the shadow operators, that you should think of as local and satisfies all the nice OP properties. The way to test this would be to understand collinear divergences, then to see which operators have the right type of singularity structures that you need for a local operator to have. We haven't done that yet. We are looking next time. Okay.
I missed how you selected J, right? So, but you wrote down is the word identity for anything.
Yes. So the point is that this is what I know.
Yeah.
This is what I want to construct. I want to construct from S some operator J such that this is true. Now I could go from here to here very trivially if, for instance, if I had some insight. For instance, if I knew that the dimension was even. If I'm sitting in even dimensions, then I know that there's some number of derivatives on this log can convert it into a delta function. In particular, the Laplacian to the power d over 2 acting on log is a delta function. So I could just start from this thing, act on both sides with Laplacian to the power d over 2, which is a sensible operator in even dimensions, and then I can obtain what the current is. But you can't do that in odd dimensions. So how do I work out what the current is in odd dimensions? The easiest step to do is to go backwards. Since I know I want to construct this, let's say I have an operator that does this, but then from here I can always construct this, right? Because I just multiply by log. Once I know what is S in terms of J, then if we're lucky, we just know how to invert it. And in this case, we were lucky because the relationship was a shadow transform. And we know that 2 shadow transforms is equal to 1, up to a number. So we know very well how to invert shadow transforms. And we would not have guessed it from the beginning because it's a very non-local operation. Like, why should I guess that I take this, I do some crazy non-local action on this, I end up getting a delta function. So that's why this was the easier way to go. But again, for many reasons, we shouldn't be surprised. If I had started from that perspective, shadow would have been obvious. If I look at all of these dimensions, the first guess would have been shadow. So, there are many things point to that. This is how we first realized it. Yeah.
Practical question. Suppose I compute these correlators in CFTD. What am I supposed to do to get the answer, non-perturbative answer for the amplitude in S matrix, say, in Minkowski D plus 2?
Yeah.
I mean,
so
what is the roadmap? What do I have to do?
Yeah. So the first roadmap is, so firstly, to work with primary operators, you have to do this Mellon transform. So the first step, so I start with CFT. Which has a bunch of, so CFT correlation functions parameterized by x1, delta 1, x2, delta 2. Suppose I know this for arbitrary delta 1, arbitrary x1.
Good.
And I just do a Mellon transform in delta. So delta gets transformed to omega.
Consider it done.
That's the S matrix. That's it. That is the S
In one
matrix.
shot.
But you have to do an inverse Mellon transform.
But this gives me S matrix in Minkowski D plus 2.
Massless, at this stage, massless S matrix, because it's parameterized by omega 1 and x1. Right? That's all you need. The S matrix is a function of the energy.
Is there some
and
integral over tau involved in this?
Well, the Mellon transform, the inverse Mellon transform is some complicated integral in complex space. So you have to firstly know
complex
how to
space of what?
of delta.
Of
You have
delta.
you have to analytic. Well, in fact, it turns out it's the principal series. So what you really need is you need to know all the correlation functions on the principal series for principal series representations. Then you have to do the inverse Mellon transform, which is some contour on the principal series.
Have you guys done that already?
It's been done for some, not we, but it's been done for 5-4 theory. Like they took the 4-point scattering amplitude in 5-4 theory and the one tree level and then one loop, and they've tried to follow this procedure.
This procedure.
Yeah, they've got it.
Who is that?
It's the same, just looking for paper now.
Yeah, it's referred in. I'll refer to it in a bit.
Okay, we'll look at those. Okay.
So, this is not a question. Like if the S matrix is weakly coupled, is it then leading to a weakly coupled?
No, very good.
What's the question again?
Is the S matrix
Basically, it's just a weak duality.
is it a weak duality?
Or is it
sort of-
big strong?
That's what I think that's the question. I'm not really sure. I think it looks like just it's a weak duality, which probably just maybe that's not as thoughtful.
It's not a criticism. I was just
Yeah.
trying to understand. So like I could take, like you were saying, phi to the 4 theory, look at the S matrix perturbatively, then get from that some CFT
Yeah.
in 2 dimensions.
Yeah. What is not known, however, so yeah, the point, it may be because we don't actually have any examples. So the point is that what has been done, you take scattering amplitudes in phi4 and you just do the Mellin transform. You get some set of correlators, right? Which is parameterized by lambda, that's lambda phi4.
Right.
Now lambda I'm taking to be small. Now the question is, what CFT can reproduce those correlation functions?
Right.
And is the parameter in that CFT lambda, or let's say 1 over lambda?
I mean, it's some CFT, it's just not an identified CFT.
It's not an identified CFT. Yeah, and what we would have to check is that in that CFT, is a lambda expansion a weak coupling expansion or a strong weak coupling? We just don't have any.
Can you answer a question like what's the central charge in that CFT? Maybe not
No,
specifically right
no.
now, but could one answer that?
Yes.
And presumably it's going to be proportional to lambda, like
Well,
first order.
no. Well, the first question
Maybe
you should
not.
straight away ask. Well, phi4 is not good enough. As I said, well, I didn't yet get the time, but the stress tensor exists only if I have gravity, just like alias. You need
Oh, of
gravity.
course.
So phi4 theory, of
Right.
course, will not do it for you. You need the soft graviton theory. So then you need to consider, in order to find the central charge, you need 2 insertions of the stress tensor to compute that, which means 2 gravitons. Problem is that, and then you need to take their soft limits. Problem then is that those soft limits don't commute. So there's no well-defined notion of what insertion of 2 stress tensor even means. So there's various questions that is unanswered and some ambiguities. That being said, there's some issue already. The question you might ask is the central charge is a number. There is absolutely no dimensionless quantity that you can construct. I don't have a radius anymore. I only have G Newton, suppose, in the gravitational theory. How could I possibly construct a dimensionless number out of those things? So either it's just literally just a number, like 1 or 12. There's a reason I said 1 or 12. Both have been conjectured. Or it's something to do, at least in 4 dimensions, it might have something to do with the IR cutoff that you have to introduce to even define S matrix amplitudes, even if they're finite at the end. It turns out that, and as I said, the subleading soft theorem is infrared divergent, so it does depend on the infrared cutoff. In which case, the central charge might be whatever dimensionless combination of mu and G newtons, which is also being conjectured. But in that case, it could be that, but the overall coefficient might still be contain interesting information. Okay, so I will just finish by also just telling you the story for the stress tensor. After all, the talk was titled stress tensor. But the story is really identical. So it's just an extra set of indices that I need to put on everywhere. Okay. So. Okay. So here in this case, I have a graviton which contains 2 indices, AB, because it transforms on the symmetric traceless representation of SOT. The symmetric traceless tensor on this side. And on this side, it turns out you have something that goes like 1 over omega. That's of course the leading Self-Graviton theorem that Weinberg worked out. I don't care about this particular one today. But there's an order 1 term which looks like -1 k pk mu epsilon a b mu j k mu nu. Let me look at the indices, clearly don't match up. Of course, what I meant is mu, 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 q, lambda, j, k, mu lambda. Yeah, acting on So that's the tensor structure. That's just the graviton polarization. It has two little group indices and two space-time indices. Okay. So we can work out insertions then of what I'm calling the subleading self-graviton operator, which is basically the operator that will extract this piece out. So that's defined by taking OAB. But over here, what I do is I multiply by 1 plus omega del omega. So what this operator does over here is 1 plus omega del omega kills this pole. And then I just take an omega goes to 0 limit to kill off all the higher order pieces. I'm left over just with that. So this insertion, BABX, has the following. It has 3 tensor structures, and which is exactly the right number. So it has the following 3C, AB. So there are 3 sort of structures with xk. You might have expected this because after all the angular momentum tensor is appearing here. So it needs to act in the conformal directions. So one of them was translations. One of this is the scaling transformations. The spin transformations. So now from this I want to construct a stress tensor, an object which has indices TAB. But we have exactly the right number of structures because in a CFT, a stress tensor, there are 3 ward identities that we have to play around with. In the divergence of the stress tensor precisely has this derivative structure. The trace precisely gives us the scaling dimension, which is omega del omega. And the antisymmetry gives us the spin. So we have 3 ward identities, all of them with exactly the right structure with delta functions. You just multiply. I didn't tell you what P is. It's some crazy tensor structure. It's not illuminating. It's some fixed, it's some known tensor structure. But so you just multiply by these various tensor structures with the 3 ward identities. You add them all up, and interesting properties of PCAB are then utilized, and the result is that TAB is the shadow transform of TAB. Okay, just as expected. And again, you can look at our paper for the tensor details of the indices, but it's really not illuminating, I think. Okay, so, well, there you have it. So we have a stress tensor. Rather, what I mean, in other words, of course, this is exactly what I should mean is that because the trace of the stress tensor is fixed by the ward identity. The antisymmetric part of the stress tensor is also fixed by the ward identity. So the only unfixed part, which is really plays a crucial role, is the traceless symmetric part of the stress tensor. So BAB itself is a traceless symmetric operator. So and its shadow transform is the traceless symmetric part of TAB, which is the non-trivial thing. Everything else is just fixed by the ward identities anyway. Okay. I think that's sort of, all what I wanted to say. One thing I just wanted to add, there is a reason I sort of skipped this first piece. You might have thought that's the easiest thing. Why shouldn't I start with the leading soft guy first? But you see the leading soft guy, as we know, sort of the symmetry associated to it is translational invariance. And it therefore becomes very convoluted in this picture because I'm trying to make Lorentz group manifest. So that's why this subleading one was very easy to work with. The leading one is actually much harder. We don't yet know if there's a nice interpretation in terms of currents. And we should expect that because the leading one, unlike all the others where I have sort of, where I can define the fields on one slice because rotations just moves around in this slice and charge, I mean U1 doesn't really affect it, doesn't have anything to do with geometry. That operator, the leading operator, will have to move you in this direction. And so it doesn't really have a nice interpretation as an ADS field. It purely sitting in ADS. So we have to be much smarter about that, if even there exists, but it must have some interpretation because it's still universal. We just don't know whether it has an interpretation in terms of a current. Okay, so I think I'll just stop there. Yes, I'll just stop there. Thank you very much for listening.
Any questions?
So how is momentum conservation in the bulk reflected on the CFDs?
Well, as I said, I'm not really sure, but I can tell you, for instance, in Mellon space, it maps delta to delta plus 1. So in particular, it's telling us that if I give you some set of correlation functions, a bunch of deltas, then the corresponding ones with all of them shifted to delta plus 1 should be equal to that. That's how it's reflected from the CFD perspective, which is very different. So in a CFD, when you typically think of CFDs, you often say, just to make it well-defined and nice, you want finitely many conformal primaries. But here, clearly, you cannot have finitely many conformal primaries, because if I have a conformal primary with dimension delta, you must have another conformal primary with dimension delta plus 1. Right? So you necessarily must have some infinite number of fields. Basically, as it had to be the case, right? Because I'm going 2 dimensions lower, so that extra dimension has to be hidden somewhere, and just hidden in the fact that you have infinitely many operators that you're discussing, talking about. So that's how it's reflected. Maps you from one primary representation to another. There might be a better way to organize. In fact, I do think there's a better way. Instead of just talking about CFT, you should probably just talk about representations of the BMS algebra, which is extended, which has also been said, but that's mostly been studied in 3 dimensions, but there's certainly something non-trivial. So I think if you organize all of your operators under BMS representations, of which the conformal group is just a subgroup, it's probably a better way to organize as an organization principle.
So how the statement is consistent with the fact you said that all operators are on the principal series?
Yes. So in Mellon theory, Mellon transform theory, you have this so-called, what's called the fundamental strip, in which your let's just do standard Mellon. I just have a function, which is, and I do it with Mellon transform. Its Mellon transform is completely analytic in this so-called fundamental strip, just some strip, and away from that it has poles and all sorts of other crazy non-analytic structure. However, what can often happen is that there are many different strips. The fundamental strip is the one in which it's well defined, but I can analytically continue to different strips. And what this translation is doing, I think what this means is that you actually have infinitely many sort of quote-unquote fundamental strips. The principal series is the fundamental strip, and then I take this delta goes to delta plus 1, maps you from this fundamental strip to the other strips. And in fact, Mellon transform theory is super fascinating, by the way. Moving from one strip in which it's analytic to a different strip in which it's analytic, the difference between the functions there captures precisely information about the singularity structure in Mellon space, which in the dual space, in this case the energy space, basically captures all the information you need to know about asymptotic expansions. So soft expansion, but also high energy expansion. So somehow, even if I only put in information about soft expansions of a